Here, we see a live digital audio stream operating within strict microsecond tolerances. The environment is stable. Then, a memory allocation spikes during the real-time render thread, and the system experiences a catastrophic silent crash. The root cause of this failure is not a complex hardware fault or a network timeout. It is the most universally used foundational data structure in the entire language, the standard Swift array. To understand why this happens, we must examine how standard arrays handle capacity growth. When an array runs out of space, it relies on an implicit geometric resizing mechanism. It allocates a larger block of memory behind the scenes and copies existing elements into the new space. This 2D timeline graphs the execution speed of that process. While most append operations register as a stable, flat line of constant time, an array boundary expansion instantly triggers a massive vertical O of n latency spike. The execution time degrades linearly based on the exact number of elements being copied. In application development, this amortized complexity is invisible, but in deterministic bare metal environments, like an audio kernel or a secure cryptographic server, missing a microsecond execution deadline forces the thread to drop data entirely, leading to system failure. The mechanisms designed to make Swift's standard array ergonomic for general application development make it a strict liability for bare metal determinism. Beyond execution spikes, modern systems programming introduces a second challenge: managing resources that cannot be duplicated. A secure file descriptor or a unique system socket can only have one active owner at any time. Swift's standard arrays manage their memory footprint using copy-on-write semantics. Multiple variables will share the same underlying heap storage until one of them mutates, at which point the array duplicates itself to maintain value semantics. Let us observe this mechanism applied to a non-copyable resource. Here is a block of memory holding a single secure socket. If a copy-on-write operation duplicates the surrounding array, we are left with two distinct pointer paths routing back to the exact same physical node. The failure occurs at the end of the system lifecycle. When these duplicate array containers fall out of scope and are destroyed, they both trigger their deinitialization routines. Two execution signals are sent to terminate a single resource. This creates a fatal double close bug. The system attempts to terminate a connection that has already been severed, corrupting the memory state and crashing the application. The Swift evolution team evaluated and rejected modifying standard arrays with runtime dynamic checks to assert uniqueness. Query incopyability at runtime introduces non-trivial overhead to every array mutation, which slows down generic execution paths for all users. Retrofitting copyable containers to hold non-copyable resources is a technical dead end. Solving this required shifting away from runtime checks and towards strict, compile-time static enforcement. Swift Proposal 0527 applies the non-copyable protocol directly to the container itself, moving beyond the initial model of only restricting the elements inside. UniqueArray provides dynamically resizing heap storage, locked inside a strict, non-copyable bounding box. It can only have a single exclusive owner. Variables exchange it using explicit move semantics. Assignment physically transfers ownership and consumes the original variable, bypassing copy-on-write branches entirely for unique, unshared allocations. However, systems programming requires balance. Developers need low-level performance isolation, but they also require zero-copy interoperability to pass these arrays back into high-level standard APIs. In the UniqueArray layout, a structural compromise exists. It carries two extra header pointers for class-type metadata and reference count tracking. This paradoxical metadata is required, so a standard array can safely adopt its storage in constant O of 1 time without triggering a memory reallocation. UniqueArray accepts a minor constant memory footprint tax per instance. This deliberate trade-off bridges the gap between low-level performance code and high-level application logic. Even with exclusivity guaranteed, environments like embedded firmware or audio kernels prohibit any dynamic heap allocation or unexpected background latency. For absolute determinism, Swift introduces RigidArray, a non-copyable, non-allocating, fixed-capacity heap container. RigidArray alters standard storage logic by stripping away upward geometric padding. It allocates its storage exactly once during initialization and never resizes implicitly. Watch what happens when this RigidArray buffer block hits maximum capacity. A new data element attempts to append itself, but is violently rejected. Instead of expanding, the system triggers an immediate runtime trap. This rejection forces rigorous upstream capacity planning. It treats capacity overflow as a fatal programming error rather than a scenario to be quietly managed. The sole exception to this rule is the manual reallocate API. This method replaces the buffer with a newly allocated block of the exact requested capacity, occurring only at developer-defined execution points. This comparative matrix details how other systems languages handle similar constraints. While Java's trim to size and Rust's shrink to fit restrict reallocation strictly to shrinking the buffer, Swift unifies both growth and shrinking into this single explicit execution point. By completely removing dynamic flexibility, RigidArray provides the zero-latency execution guarantees required by the most demanding real-time threads. These strict containers introduce a mechanical problem. We must populate them with data safely, without triggering the very temporary heap allocations we just eliminated. Swift solves this through the span ecosystem, a suite of non-escaping types designed for zero-copy memory management. For initialization, it relies specifically on OutputSpan. An OutputSpan bounding box acts as a bounds-checked view over uninitialized memory. Developers actively inject data directly into the space. If initialization stops early, the array must clean up the uninitialized gap by shifting the subsequent trailing elements backward. This cleanup process penalizes incomplete promises by adding a linear time overhead penalty to the operation. The design prioritizes complete, predictable initialization. Notice what happens when this output span attempts to move out of its local scope and into an asynchronous thread. A compiler lock instantly drops down and terminates the action. Output span is restricted to synchronous closures. Preventing the span from escaping is the only way the compiler can statically guarantee the lifetime of the underlying heap allocation. Passing it asynchronously risks modifying memory that no longer exists. By combining spans with non-copyable containers, Swift removes the burden of runtime garbage collection and replaces it with a compile time guarantee of memory safety. This architectural trade-offs matrix details the contiguous storage ecosystem. Developers now select specialized tools instead of a single one-size-fits-all array. Standard array relies on implicit expansion and runtime checks. In contrast, UniqueArray and RigidArray rely on static compile time exclusivity for their performance. Selecting a container now requires mapping the specific execution constraints of a thread, such as its tolerance for latency, to the memory layout of the storage. With version 6.4, the Swift standard library expands into low-level primitives, providing the tools necessary for strict resource control alongside traditional application-level ergonomics. With the integration of UniqueArray, RigidArray, and the strict zero-copy boundaries of the span ecosystem, developers are finally equipped to write deterministically safe, bare metal systems code entirely within Swift.